So yeah, there are a lot of interesting things, capabilities that we discover from the model. For example, it merges the visual capabilities with coding capabilities. So a lot of new things just emerge out of it. It can read a video and then produce a website that sort of replicates or style transfer the original video. And all of this are due to successful and stable training at the pre-training stage. So this is also one of the most beautiful curves that I observed in my life. So this is the training curve of the K2.5 based model. So as you can see, it went through over 15 trillion tokens, and of course in K2.5 we additionally trained another 15 trillion tokens. And the entire the training process is just so stable. There's no loss spike, especially when we introduced this new muon optimizer. We didn't observe any spike. And this smooth, stable training process produces a very stable outcome, a very strong base model that we can fine-tune on top of it to achieve new capabilities as we introduce and saw in the video. And this is also, of course, trained on NVIDIA H800 GPUs, and each node in this H800 cluster contains 2 TB RAM and 8 GPUs. They are connected by NVLink. And another key innovation of Kimi K2.5 is that it is the first open model with native joint vision text capabilities. So if you look at previous open models, usually their visual capabilities are added on top of a text base, meaning that, for example, if you train the text models for 20 trillion tokens, and then on top of it, you do another 2 trillion, sort of a post-training process to add additional visual capabilities on top of it. But for K2.5, it's different in the sense that we fuse the training process of vision and text from day one. So it's called early fusion here. We start from 0% of the progress. So from day one, we're going to merge the vision and text tokens, and as shown in our preliminary experiments, it outperforms late fusion. And some of the new capabilities that we observe also come from this training recipe. For example, if you want to do vision to kill, you really have to merge vision and text into a single brand to achieve that. If you separate these 2 brands, it's not going to happen. You have to align these 2 modalities into a shared embedding space, a shared representation space, so as to achieve this. And another interesting thing that we observe is that these 2 modalities can actually enhance each other. So that's been long been a challenge that if you add vision capabilities into a text model, it's going to somewhat hurt the text performance. But here we found that if you train it properly, these 2 modalities can actually enhance each other. So this is one of the key findings that we observe in our training. So first, vision improves text. So this is so interesting. So before vision RL, the performance in the first column, and then we have the performance after vision RL. So here, vision RL refers to a process that we only use vision tasks. So there is no text task involved here. We only have vision tasks. For example, we teach the model how to count, how to answer some of this visual QA problems without any, for example, math, any coding problems in this space. But we observe that it's going to improve the performance for even reasoning heavy text tasks. And on the other hand, text also improves vision. If you have a very strong text base, you actually don't need any vision SFT data in the training process. And this is the approach that we adopt. So it's called zero vision SFT. Basically, we have basically zero vision SFT data. And the only SFT data that we have is the text SFT data. And then we do a joint RL over text and vision. And you can see that we can achieve almost state-of-the-art performance across the board on vision tasks without any vision data. So it's clear that if you have a strong text base, it's also going to improve the vision if you align these 2 modalities into a shared space in your pre-training. And also, these are some of the examples of as I was showing in the video. So it demonstrates strong capabilities of visual design and front-end coding, and this also emerges from our vision text pre-training. So after all this, so these are all about Kimi K2.5. And as probably you probably know, we released our new architecture yesterday in our tech report. It's called Attention Residue. So here I'm also going to briefly talk about our new work, which serves as a sneak peek into our next generation architecture that we're probably going to adopt in our later models. So here the motivation is quite simple. Can we apply some of our techniques that we use in the temporal dimension, and we just take some of the inspirations and then apply it to the depth dimension? So and it starts from this residual connection. So I still remember listening to Kimi's talk at the tutorial in ICML 2016, 10 years ago. So it was a brilliant idea. So basically, before ResNet, nobody was able to train deep networks. If you increase the depth, if you increase the number of layers for neural networks, nobody was able to train it because you observe this gradient exposure, gradient vanishing, all these stability issues. But then after the introduction of ResNet, we can train an arbitrarily large number of layers. You can stack as many layers as you want, and you don't have to worry about the training stability issue and stuff. And as discussed in Ilya's talk 2 years ago, it basically says that residual connection is a variant of LSTM, but just rotated 90 degrees. So how do you understand this? If you look at LSTM, it's a variant of recurrent net, right? And it's a recurrent model process. So we're going to take the hidden states from the last step, and then we're going to have some gating mechanism, some function to produce the current state, right? And if you look at the depth dimension, the residual connection is basically the same. We're going to take the outputs from the last layer, and then we're going to apply some sort of function on top of it to produce the current outputs of the current layer. It's just the formulation is different. For example, for residual connection, we're going to use a fixed addition. We're going to have this. We're going to add the previous hidden states with the current output. It's just the formulation that's different, but the basic idea is the same. It's a recurrent net applied in the dimension of depth. But on the other hand, we can think about reformulating this function. Instead of having an LSTM, can we have an attention in the dimension of depth? And it's going to create new possibilities because attention has been demonstrated to be so successful in the transformer era. So what we're going to do is not just to take the last hidden state, but we're going to consider all the previous hidden states and use the attention operation, the attention mechanism, to assemble and aggregate all of these previous hidden states to compute the current state. So this is exactly attention rotated by 90 degrees. It's sort of, we view it as a natural generalization of residual connections in the LSTM analogy. Okay, and here is the detailed formulation. So on the left-hand side is a standard residue. As I said, it's basically LSTM rotated by 90 degrees. And the second figure is attention rotated by 90 degrees. So what we do is to collect all the previous hidden states and have a simple attention operation on top of it to produce the current layer's outcome. And of course, to increase the efficiency, to reduce the infrastructure, for example, communication and memory overhead, we also design a new variant called block attention residue on the right-hand side. So basically, the idea is also simple. We're going to divide all the layers in the neural networks into multiple blocks. For example, each block can contain, say, 16 layers, or it can contain maybe 4 layers. And then for each block, we're going to apply this attention residue only on the outputs of each block. But within each block, we still adopt this standard residue. So this is going to reduce a lot of overhead while having minimal loss in terms of training accuracy. And these are some of the impressive results that we achieved on this new architecture. So on the scaling law, we can improve the token efficiency by 24%, meaning that if you have 50 trillion high-quality tokens, now you just magically have over 60 trillion tokens. And then for the validation loss, you can also observe that it's consistently lower than the original curve, demonstrating this stability across optimization, and also achieves the best improvement on some of this coding, math, and reasoning-heavy tasks, as shown in the benchmark results of GPQA, math, and human eval. So the entire community keeps moving forward, and we're happy that we're able to contribute to the community with new technologies. And some of these technologies have been sort of standard and de facto for a long time. But as you can see, we still see a lot of opportunities to improve it, to have revolutionary new design to achieve better performance. If we multiply all these gains together, you can actually have a much better model. So Adam was invented in 2014, and now we scale an open source MuonClip, a drop-in replacement for Adam. And I'm sure that if you train a transformer LLM, it's going to be much better if you use MuonClip instead of Adam. And attention was invented over 8 years ago. And then now we have Kimi linear, which is a linear version. We don't have to use full attention across all layers. We can have linear attention that performs better on short, long contexts at the same time. And also, residual connections are now also challenged. We scaled an open source attention residue. So I think one of the interesting things about our era is that we sort of adopt a different mindset for doing research. So if we go back to 10 years ago, it's mostly about publishing a new idea. But then I think the lack of the rigor of the experiments is very hard to produce solid experimental results. But now we have this scaling ladder. We have enough resources to train the model and run it on at different scales. We can have a whole set of benchmarks to measure the progress. So it becomes easier to make confident and solid conclusion out of it. And this is one of the reasons why we are observing new progress on these ancient techniques. And I'm sure that we'll see more and more, especially in the open source community. I think we're going to have more and more even better architectural and optimization improvement in the next few years. All right, so to summarize, we're going to keep scaling our models. And so these are 3 dimensions. For example, we see different architectures and optimizers that optimize all 3 dimensions, and we'll keep see new dimensions for scaling. Agent swarms is not the end, and we are glad that we can move forward with the entire open source community to achieve better and better intelligence. Thank you so much.